Alright, welcome back guys. We're going to go ahead and finish up 6C, so the second half of working with the normal distribution. Okay, so this last example, what we did was we assumed that this normal curve represented the distribution of SAT scores. Okay, and the mean was 500, so it's here in the middle. And the standard deviation was 100, and so we just marked these off. One standard deviation above the mean would be 600, and then 700 and 800. And we also talked about using this 68, 95, 99.7 rule that we can talk about what percentage of the distribution will be within one standard deviation of the mean, within two, or within three. Okay. Or in the context of the SAT, you could say that between 400 there will be 68% of test takers who score anywhere from 400 to 600 on the SAT, and then there'll be close to 95% of test takers who score anywhere from 300 all the way to 700. So that's within from two standard deviations below the mean all the way up to two standard deviations above the mean. And that's kind of where we stop. So now we're going to kind of look at some more practical examples. So example 4, it says detecting counterfeit coins. So this is an interesting example. It says vending machines can be adjusted to reject coins above or below certain weights. Okay, and the weights of legal U.S. quarters are normally distributed. So that just means if you took a big sample of U.S. quarters and recorded their weights and made a histogram, it would have this bell shape. Okay, and it says the mean or the average weight of a quarter is 5.67 grams. And the standard deviation is 0.07 grams, or in other words, 7/100ths of a gram. Okay? And so the question says, if a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of legal quarters will be rejected by the machine? Okay? And it says draw a picture. So in almost all of these guys, you want to draw your normal curve, just like I have here. And I'm going to start marking off 1, 2, and 3 standard deviations, values for 1, 2, and 3 standard deviations, both above and below the mean. Okay? And you pretty much have to do this for every one of these. All right, so the mean is 5.67 grams, so that'll be right there in the middle. And the standard deviation is this amount, 0.07 grams. So what I'm going to do is to find these values above the mean, I'm just going to start adding the standard deviation to this number. So if I add 0.07 to this, my next value would be 5.74, and then 0.07 more would be 5.81. I think that's all I'm going to do. Okay. Now let's do the other side, except on the other side we'll be subtracting the standard deviation. So if I subtract the standard deviation from 5.67, that'll take this down to 5.6. And if I subtract again, that'll take that down, or 5.60. That'll take this down to 5.53 grams. And so notice this number and this number are familiar. Okay? So it says if vending machines are adjusted to reject quarters that weigh more, okay, so the ones that weigh more would be in this area. I'm going to go ahead and shade this in. And weigh less than 5.53, so that would be this area over here. Okay. All right,
So in other words, we're trying to figure out, well, what percentage would these two areas comprise of this total curve here? Well, guys, we have to use that rule again. This value, 5.53, is 2 standard deviations below the mean, and 8.81 is 2 standard deviations above the mean. And that rule tells us that between 2 standard deviations from the mean, we have 95% of our data. Or in other words, 95% of the quarters that go into this vending machine are going to weigh anywhere from these two values. Okay? So, what we're trying to figure out what percentage of the coins are going to fall either below or above those two values. Well, under this entire curve, there's 100% of the data. So if 95 is between these two values, then that must mean 5% is in those two tails. Or in other words, 100% minus the 95% leaves us with 5%. Well, that's 5% in both tails. So that means that in each of these tails, there would be 2.5%. Okay? You divide 5% by 2. Whoops. And so this is the way you have to kind of figure these out. Okay, so in other words, the quarters that are below this value and above this value are 2.5 plus 2.5, which is a total of 5%. So 5% of the quarters will be rejected. And this is actually how things work. Those vending machines can be calibrated. Okay? If they weren't calibrated, guys, you know, for weight and things of that nature, you could just insert counterfeit coins. And that's probably why, if you've ever had this happen to you in the past, certain vending machines may reject your coin, and it's probably because it's outside of those two bounds. Because of the manufacturing process and everything, you know, we can't expect that a quarter would weigh the same every single time. There's always going to be variation in our data. And there's variation. It may be very slight in the weight of quarters or coins. So 5% of those quarters are going to be rejected. Okay? Alright, so let's take a look at another one. So we're doing the same thing here, guys. It says, consider an exam taken by 1,000 students for which the scores are normally distributed, and the mean is 75 and the standard deviation is 7. Okay, so on this test, the mean is a score of 75 and the standard deviation is 7. So before I even start trying to answer any questions below, I'm going to go ahead and start labeling this. So if the mean is 75 and the standard deviation is 7, then that means one standard deviation above the mean would take me to a score of 82. And then 7 more would take me to 89. And then 7 more would take me to 96. Okay. Now on the other side, I'm going to subtract 7. That'll take me down to 68. Minus 7 again will take me down to 61. And minus another 7 would take me down to 54. Okay. So now once you have this labeled, now we can start figuring out how to answer these. So it says, suppose we want to know how many students scored above 82. So what does that rule tell us? We have to see where 82 is with respect to standard deviation. So 82 is right here. It's one standard deviation above the mean. Okay. So this rule tells us that from one standard deviation above the mean to one standard deviation below the mean, we have 68% of the data. So how could we figure out how much data is going to be in the right tail and in the left tail? Well, we do it the same way we did the last one. We know there's 100% of the data under the curve minus the 68 that's in the middle. That leaves us with 32%. So that 32% is split on this side, okay? And on this side, okay? So between these two tails, there's 32% of the data and there's 68% in the middle. We're trying to figure out what percentage is above 82, so that would correspond to this region here. I'm going to shade it. This whole region. Okay? Well, once you know the region that you're considering, then you can actually figure out the percentage. Okay? Well, this is just one of those tails. We know that both of these tails contain the other 32%. So if you divide 32 by 2, that's going to tell you what's in just one of those tails. And in that case, it's going to be 16%. So we can say that within that one tail, there's 16% of the distribution. Or in other words, 16% of the students scored above 82. Now that's actually not what the question asked. The question asks how many students scored above 82. Well, we know 16 of them scored above 82, but we need to figure out what 16% of the number of students that took the test. Okay, so that's our last step here. 16% of 1,000. Okay, remember you would change that 16% to a decimal and then multiply it by 1,000. If you do that, you are going to get 160 students. So 160 students scored above an 82. Okay, or in other words, you could say 160 students scored one standard deviation and higher above the mean. All right, there's a second part to this question. Suppose we want to know how many students scored below 61. Okay? Well, we're going to have to do something very similar, guys. Below 61 would be right here and to the left. So we'd have to try to figure out how much area is in that little tail. Okay? So I'm going to do some erasing here because we're done with the previous one. Okay? Alright, well, this 61 right here corresponds to 2 standard deviations below the mean. And the rule tells me that from 2 standard deviations below to 2 standard deviations above, we have 95% of the data. So 100 minus 95 is 5%. Okay? So again, 5% is in both of these tails together. But we're not considering both of them like in that previous example. We're considering just one of these tails. So if you divide that by 2, then you get 2.5%. And that's the percentage of students that scored below 61. Okay? So the more of these you do, guys, you'll see these numbers pop up over and over. So there's 2.5% here. From one standard deviation above, there's 16%. Okay, and then 16% over here. So you're going to end up seeing the same values. All right, well, there's 2.5% of the students that scored below 61, but how many students is that? Well, we need to figure out what 2.5% of 1,000 is. And so you do it the same way. Turn it into a decimal. and multiply it by 1,000, and that's going to give you 25 students. Okay? This is kind of interesting. So 25 students scored below 61. I like this because I think it's kind of like figuring out a puzzle. You know? I think we've got one more here. Example 6. This one's interesting too. I like this. It says actual lengths of pregnancy times for a particular species of mammal are nearly normally distributed. About a mean pregnancy length and a standard deviation of 17 days. About what percentage of births would be expected to occur more than 51 days after the mean pregnancy length? Okay? What you may notice about this one is that they don't actually tell us the mean. And they don't need to. It's not important. Okay? So again, I'm going to go ahead and I don't have a graphic in here, so I'm going to sketch me a normal curve. And the mean is right here in the middle. Okay? Now we don't know what it is, but we don't need to know. What is important is that the standard deviation is 17 days. So that means one standard deviation in pregnancy length above the mean would be 17 days more than whatever this value is. Okay? And then another 17 would take this to 32. Not 32, but 34 rather. And then another 17 would take us to 3 standard deviations above the mean, and that would be 51. Okay? Now on the other side, one standard deviation below would be 17 days less than whatever the mean is. And these would just be negative numbers, basically. Okay. So we don't actually have to know the mean to figure this out. Now the question is about what percentage of births would be expected to occur more than 51 days after the mean pregnancy length. Well, 51 is over here. So more than 51 would be the area in that little tail. Okay? And that value is 3 standard deviations from the mean. So that rule tells us that from 3 standard deviations below to 3 standard deviations above, we have 99.7% of the distribution. Okay? So then what would be in the 2 tails? Well, whatever 100 minus 99.7 is, which is 0.3. So 0.3% of the distribution is in these 2 tails. But what's in just one tail? Well, you've got to divide this by 2 again. So hopefully you can start to see these are really the same problems over and over and over. You're just trying to figure out how much area is in one tail or sometimes both tails. And this would be 0.15%. Okay? That's the percentage of births that would be 51 days above whatever the average pregnancy term is. And I would be willing to bet that the gestational terms in human females is normally distributed as well. Okay? Now, that can be a little problematic because doctors won't actually let you go beyond a certain number of weeks. And so there would actually be a cutoff there. Okay? But theoretically, they would be normally distributed with a mean being, 38 weeks or 40 weeks, something like that. Because, most babies will be born around that time naturally, and then you'll have some that are naturally born that come sooner, and some that naturally come a little bit later. But then, like I said, normally they won't let you go. I think it's more than 41 weeks before they they will induce labor. But anyway, those are a few examples. I know these problems tend to be pretty challenging for students, but guys, draw yourself a diagram the way I've done. And you're going to be using that 68, 95, and 99.7 rule. All right. Well, that's it for chapter 6. And in the next video, we'll be working on the one section in chapter 7 on probability.